All right. So hi everyone. So let me recall you what we did last time. So last time we briefly did some reminders on the category of simplicial sets, and in particular the adjunction that exists with topological spaces. So given by on the one hand geometric realization, on the other hand the singular set. And then we described the Quillen model structure on this category. So the weak equivalence is something which is sent to a weak equivalence under geometric realization. Fibration is a can fibration, which is something which has a right lifting property with respect to these inclusions. And finally, cofibrations were injections. And I said that this category is cofibrantly generated by, on the one hand, these generating cofibrations, the inclusion of a boundary of a simplex inside the whole simplex. And for generating acyclic cofibrations, we had these horns included inside the full simplex. All right. And so we had to check a bunch of properties to prove that it's a cofibrantly generating model category. So we had well, first of all, we had the 2 out of 3 property. We had stability under retracts and so on. We had smallness of these things, which we proved. We had, of course, limits and colimits, which are defined pointwise. And finally, we proved this first lemma, which says that cofibrations are indeed generated by this set I, and that moreover, we can prove that they are all I-cellular morphisms, which is to say that any inclusion of a simplicial set is built by gluing cells in some way, just like a CW complex. All right, so are there any questions about all of this before we continue proving this theorem? Or about simplicial sets in general, I guess? No. All right. So we are going to check the other 3 conditions. The last one is going to be actually very difficult. And compared to my notes, I'm actually going to, so in my notes, I just said that it's difficult and I won't prove it. Here I will prove part of it. So it's not in the notes yet. But I will have to make a small detour through what we call anodyne extensions. But anyway, you are going to see. So we have 2 lemmas which are not that bad. So the first one is that J cell is included in acyclic cofibrations. All right, we have to check that if we build something inductively from J, so we glue simplices along horns, then we get an acyclic cofibration. So let's prove this. It was one of the conditions to apply the theorem about cofibrantly generated model categories. So first of all, J is included in C. All these maps are inclusions, right? So in particular, this we proved is equal to this thing. So any map of J has the left lifting property with respect to maps which have a right lifting property with respect to I, all right? So it follows that J cell is included in this thing here, because any class of the type blah, 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 is stable under cell. All right. If you have something which has the left, and in this case it's important, if you have something which has the left lifting property with some class of maps, then any class of map built by using pushouts it will still have the left lifting property. because to define the lifting, you have to define it using just the universal property of push-out, right? And for infinite colimits, you also use the universal property of colimit. All right. So is this okay for everyone? It's an argument we have used several times already. All right. So we have the first part of the inclusion. Now we need to prove that anything which is built from J using push-outs is still a weak equivalence, which is to say that the geometric realization of a map built from J by push-out is a weak homotopy equivalence. All right. So to prove this, first of all, the geometric realization is something that I mentioned briefly before. This is homeomorphic to this. All right. The inclusion of a horn inside the full simplex is homeomorphic to the inclusion of a face of a cube inside the cube. Right? It's not that hard to see. So therefore, so I'm going to use this notation. This is there are a lot of bars here. All right, it's composed of acyclic cofibrations in top. All right. So if you take something in J and you take a geometric realization, then you get something which is an acyclic cofibration in topological spaces, right? Geometric realization is the left adjoint, from which you can deduce that, I will write it this way. And I hope it will be clear what I mean. If you take something which has the left lifting property with respect to something which has the right lifting property with respect to J, then this is a continuous map which has the left lifting property with respect to the with respect to the geometric realization of some map in J, right? Right, and this just follows from the fact that this is a left adjoint. So if you want to prove that something has the lifting property, then you just apply the adjunction and you prove that it has the lifting property with respect to S bullet, right? So you do a little exercise, but by definition, this is given by acyclic cofibration in top, because we prove that top is a cofibrantly generated model category. And so this is the set of generating acyclic cofibrations, and therefore this is the set of all acyclic cofibrations. All right. So in particular, these are weak homotopy equivalences. All right. And so it follows that this, these are all maps which are sent to weak homotopy equivalences under geometric realization. So in particular, by definition, they are weak equivalences in our model structure. But anything which is in J cell is in this thing. So it follows that this is also true, right? Because if something is a cellular cell complex, it will have the left lifting property with respect to a map which have the right lifting property with respect to J. Because the maps that are here all have the right lifting property with respect to J, and therefore they have the right lifting property with respect to things which are built by push outs along maps of J. Right. Okay, so we have proved the two things. First of all, J cell is included in this thing here, which is cofibration, as we proved before, and they're also included in weak equivalences. Okay, good for everyone. All right, so let us continue. Second easy lemma. All right, elements of this thing here are acyclic fibrations. All right, so this was one of the conditions of the cofibrantly generated model category. So we have to prove that this is included in this. Okay. All right, so for the proof, so let P be some map which has the right lifting property with respect to I. So we have proved that P, so in particular, it has the right lifting property with respect to I cell. So in particular, P lifts against inclusions. All right. So whenever you have an inclusion, you can lift the map from P. And so in particular, P lifts against this inclusion. So P is a fibration. Okay. I know it sounds a lot like I'm not proving much, but this really follows from this lemma, right? Which is not that obvious, right? It says that you can get the full simplex from the horn by just gluing simplices. Actually, we are going to prove a little bit later an explicit description of how to get from this to this using simplices, but for now we just need some abstract result. All right, so we know that P is a fibration. Now we need to prove that P is actually a weak equivalence. So we need to prove that P, the geometricalization of P is a weak homotopy equivalence. So this was the first part. So now because P lifts against inclusions, we can also find a lift in this diagram. So you take X and you embed it into Y using this map, all right? Sorry, you embed it into X cross Y. All right, this is clearly an inclusion. Here you have X and the X. Here you have projection on Y. And here you have P. And this diagram obviously commutes, all right? But because P lifts against inclusions, and of course this is an inclusion, you can find a lift here, let's say L, from which it follows that P is a retract of Py, the projection on Y, which you can see this way. So you have this inclusion, let's call it Ix, X cross Y, X, here it's your lift, right? This map is the identity because of the commutativity of this triangle. Here you have P, and here P, Y, Y, and here it's Py, Y, the identity, and the identity. All right, and this square commutes by definition of Ix, right? And this square commutes because this triangle commutes. All right, so P is a retract of Py. So So if we manage to prove that Py is a weak homotopy equivalence, then P will be a weak homotopy equivalence because weak homotopy equivalences are stable under Rietvrights. All right. What I'm saying, weak homotopy equivalences are not stable under Rietvrights, but what we know is that the geometric realization of Py is a Serre vibration. All right. Is the projection like this, and the projection like this is always a Serre vibration. So therefore, the geometric realization of P is a Serre vibration. So if we want to prove that the geometric realization of P is a weak homotopy equivalence, we just need to prove that its fiber is contractible. So let F some base point, I don't know why, be its fiber. We have a long exact sequence which goes like this: pi n f, pi n x, sorry, yes, pi n geometric realization of x, and so on. So if we manage to prove that these are all 0, then of course this map will be an isomorphism. So we are good to go. Okay. And maybe I should say, okay, let's call F the fiber of P, and its geometric realization is the geometric realization of the fiber of sorry. So F, let's write it this way, is delta 0 cross y x. So this is the fiber of P. Of geometric realization of F is the fiber of the geometric realization of P, right? Just to have something nice, right? So we have a diagram like this. All right, this is the definition of a fiber. And so this map has the right lifting property with respect to I, and this is a pullback of it. So this map, which we can call, I don't know, pi. So pi, so P has the right lifting property with respect to I, so therefore pi has the right lifting property with respect to I because it's a pullback of I. Okay, I see that there are questions in the chat. Why is the geometric realization of a product the product of a geometric realization? Well, it's not necessarily trivial. It's some facts about geometric realization of simplicial sets. It's something that is true. But you are right, it's not trivial because in principle, geometric realization commutes with co-limits because it's a left adjoint, not limits. But in this case, it's actually true. I can look up a reference for you, but it's not something that I'm going to prove. Anyway. You can, it's probably in the book of Gers and Jardine at some page, but okay. I will get back to you on that. For now, let's focus on this proof. Okay, so in particular, pi has the right lifting property with respect to all inclusions. Okay. And so in particular, F is non-empty because otherwise it would not have a lifting property with respect to all inclusions. because of this diagram, right? This is an inclusion. Therefore, we can find a lift. And therefore, F is non-empty. All right, so you are saying that we need some assumption on X and Y. Okay, so maybe we need some assumption, but anyway, in this case, we don't need this because there is a theorem which I'm not going to prove. I'm going to need it a little bit later, but now I realize I actually need it earlier than I thought, is that this is a can vibration, and therefore geometric realization is a Serre vibration. And well, we can use the theorem at this point. The geometric realization of a Serre vibration is always of a can vibration is a Serre vibration. Okay. I guess in this case it's easier to prove. I have to think about the details back. But okay. Anyway, I'm going to state it later, but geometric realization of can vibration is a Serre vibration. This is always true. Okay. Even if we don't have that geometric realization of this splits of the product. I will try to think about it a bit during the break. Yes, it's not a trivial statement, right? It's something non-trivial, which is true. But we are going to the theorem of Quillen, actually. If you want an actual reference, you can look in RV. It's corollary 3.6.2, right? Okay, but okay, I'm going to think about it during the break. But in this case, we can use this statement at this point. Okay, where was I? So I want to prove that F is contractible. So essentially, I want to prove that pi is a weak homotopy equivalence. All right, so let F be a vertex of F, and let well, F from F to F a constant map. Okay, I hope you will forgive this abuse of notation. And we have a commutative diagram like this. So this is pi, this is simply the inclusion, and here is IGF, and here it's, well, the terminal map. Okay. So this commutes, well, it has to commute. This is a terminal object. This is an inclusion. This is something which we proved has the lifting property with respect to all inclusion. So therefore, we can find a lift here. All right, and then the geometric realization of H is a homotopy between the identity of F and the constant map equal to the geometric realization of F. So therefore, F is contractible, and therefore P is weak. Homotopy equivalence. All right. Okay, so there is another question, which is why F is the fiber of the geometric realization of F is the fiber of the geometric realization of P. So for this one, it's really like write down the definition of a fiber, and you will see that something is in the fiber of a geometric realization if and only if, right? Something which is in the fiber of this is something which is which comes from here. All right. If something is sent to the base point here, then the vertex which is here comes actually from the fiber. It's not a statement about geometric realization preserving limits. It's really like an actual statement about what the functor is. Okay, so well, modulo this little thing here, we have proved that if something has the right lifting property with respect to I, then it is an acyclic fibration. Okay, any other question about this proof? Okay. Yeah, don't hesitate to interrupt me if something is not clear. Okay, so we have one last statement to prove about the theorem, which is that acyclic fibrations actually have the lifting property with respect to I. So with respect to the inclusion of a boundary of a simplex inside the simplex. And this is hard. So we are going to prove it in the particular case where we have fibrant objects for the source and the target of the map. If the source and the target are not fibrant, then it's even more difficult, and you have to use the theory of minimal fibrations, and it would take too long to do, take until the end of the course. So I will skip this. You can look in the book of Gers and Jardine for the reference. So we are going to prove this lemma, as I said, in a particular case, and even that is going to take us, well, I guess, all of today's session. So our goal is to prove this, and in the process, we are also going to prove that the adjunction here is a Quillen adjunction. Okay. So this is our goal, to prove that acyclic fibrations have. So I will write it again. But whenever you have this map, then you can lift against any acyclic fibration. So something with geometric realization is a weak homotopy equivalence, and which is a can fibration. All right, it's not easy. Sorry. All right, so this is the part which is not in the notes, which I just skipped. So I will add this to the notes at some point, hopefully before the end of the course. But here is the proof. So the proof is going to take us, I would say, at least 1 hour. Okay. So to do this, we are going to go through Simplicial homotopy groups. We are going to go through the equivalence with standard homotopy group that you saw in the first course. But as you know, this only works for fibrant objects. So that's why I will prove this only if you have fibrant and source and target. And we are going to also see a little bit the theory of anodyne extensions. So first thing I want to talk about is enrichment and simplicial homotopy groups. I'm not going to talk much about what is enriched category theory. Some of you probably already know about it, but I will just well, give a very brief set of definitions. Okay. So let A, X be two simplicial sets. They are mapping space, which, as is common in homotopy theory, so modern homotopy theory, is not actually a space, it's a simplicial set. Is a simplicial set which is usually denoted like this. All right, defined by map n between x and y. So this is a simplicial set. In dimension n, we have the morphisms of simplicial sets. So it's something a bit complicated, right? From A cross delta n into X. Okay. So this, maybe I will write bullets just to. Sorry, this is A and X. All right, so this is a simplicial set. To get it in degree n, you take the simplicial set A, you cross it with delta n, which is another simplicial set, so you get a new simplicial set. And you look at all simplicial maps from this simplicial set into X. Okay. So for example, map 0 from A to X is simply the maps, the simplicial maps between A and X. Map 1. So the edges of our simplicial set are the map from A cross delta 1 into X, and so on. All right? And so the simplicial structure of map is induced by the co-simplicial structure of delta upper bullet, right? This is a co-simplicial simplicial set. So what I want to say is that if you have some f which goes from A cross delta n into X, and you have some phi which goes from bracket M to bracket N, you want to define phi upper star of F, which has to be a map from A cross delta M to X. So this map is simply given by phi upper star of F applied to A and some element T. Okay, maybe not T. X will be F of A phi lower star of X, where now you use the co-simplicial structure of delta bullet. All right. So is this definition okay for everyone? Okay, so this is an instance of enriched homotopy category theory. I'm not going to say much about it, but if you are interested, just look it up. It's a way, essentially, you have this thing here. So if you forget, in some sense, the simplicial structure, you get back your standard Hom sets, and then you have higher stuff. So I'm going to need a few lemmas. So something which is more or less obvious is that map from delta 0 into x is isomorphic to x. Well, the proof is simply this. But crossing with delta 0 is doing nothing. And then you have a Yoneda lemma. And I will let you check that everything that I have written here is compatible with, well, essentially it's natural in X, right? It's compatible with the simplicial structure of X. Okay. Which is, well, something you have to check. It's not completely obvious, right? You have to check something. So if you want to make sure you have understood what this space is, I encourage you to check that, how to say, this bijection here is compatible with the simplicial structure, right? Because they are not defined the same way. Here you use the simplicial structure to act on X. Here you act on delta n. So it's not directly the same. Something else which is characteristic of enriched category theories, so which is basically an enriched Cartesian category theory, if you want to get technical. You have a bijection like this. All right. So in some sense, well, not in some sense, actually, map from B is a right adjoint of crossing with B. Right? The proof is a bit of abstract nonsense. I will define two maps. One, the first way. So sorry, this is psi, this is phi, and I will let you check that they are inverse to each other. It's not hard, but just to write on the map. So let's say you have a simplicial map. It's a bit complicated, right? So you have a simplicial map from A into map from B to X. All right, so it's a collection. Fk goes from AK into map K, which is Hom of B cross delta K to X. And I want to define psi F has to be a simplicial map from B, A cross B into X. And so if you want to define it in degree n, and you have some AB here, well, I will write the formula. You take f of A. So f of A is something which goes from B cross delta. So maybe I should write the same index. So it's something which goes from B cross delta K into X, right? And so you can apply it to B, the identity of K. Okay, which is a K simplex inside B cross delta K. And the other way around, let G be a simplicial map from A cross B into X. We define phi G has to be a map from A into map Bx. So let's say we are in degree n. You have to go from an into map n, which is hom of b cross delta n into x. Okay. And so let's say you have A in an. You have to define phi g of A has to be a simplicial map from B cross delta n into X. So let us define it in degree K. It starts to become a bit complicated. So let's say you have some K simplex here. And here U is a K simplex in delta n, which is simply a map in delta from K to n. Well, you simply take, let me take GK applied to U upper star of A, B, right? So B is a K simplex, A is an N simplex, but you can apply the simplicial structure of A using U to get a K simplex, and you apply GK. And it's a bit of abstract stuff to show that these are bijections, right? That these are inverse to each other. Well, first of all, they are well defined, right? They define simplicial maps, and then that they are inverse to each other. So it's a little exercise. I will let you do it. Okay. Okay for everyone? Okay. So now we get to the difficult part. So let I from A to X to B and P from X to Y be simplicial maps. Yes, I can go a bit up. All right, so you have two simplicial maps. Then you have a diagram like this. Map from Bx, map Ax, map By, map Ay. All right, so this is post-composition by P, pre-composition by I, pre-composition by I, post-composition P. And you can check that this diagram commutes. Okay. So this induces a map that I'm going to denote like this. I upper star, P lower star. It's not a standard terminology, but I don't know if there is one. It goes from map of Bx to map of Ax cross map of By map of Ai. All right. So what is this space? This space is a couple, and a map from A to X, a map from B to Y, such that well, this is a couple FG. So this is from A to X, this is from B to Y, such that P circle F is equal to G circle I. So essentially, it's a commutative square where P is on the left and I is on the right. And what is this? This is a map from B to X, L from B to X. Basically, you can think about it as a lift, right? So you have A goes to B, X goes to Y, using I. this goes P. Whenever you have a map like this, you can define a commutative square simply by taking the composition. Okay? So this is what this map does, but just in an enriched way, right? And so we get to the big proposition. Okay. Let I be a cofibration and P be a fibration. Then I upper star, P lower star is a fibration. Okay. It's a bit hard to wrap your head around this. It means that you have a space of commutative squares like this, where P is on the right and I is on the left. And whenever you have a space of lifts, right? And this is a fibration. If P is a fibration and I is a fibration. It's a bit hard to interpret, but this one is a bit easier if either, well, I will not say it like this. If I is in W or P is in W, then I upper star, P lower star is also cyclic. So it means that you have a space of commutative squares, you have a space of lifts. If one of the two is acyclic, then you know that there exists always a lift, but it's even stronger than that. And probably in the course of Muriel-Livernay, you will see how to interpret this in terms of higher category, but essentially it means that for any commutative square, there is a unique homotopy class of maps. Right, up to homotopy, there is a unique lifting solution. Right, not only it exists, but it's unique up to homotopy. And even more than that, the homotopy between the homotopy that are compatible with the commutative diagram are unique, and so on. It's something a bit. So there is a way to interpret it like this. I will not do it. Just I will need this technical statement. But just be aware of the fact that you can interpret this in well, some way that makes sense, right? It's not a statement that comes out of nowhere. Okay. So any questions about the statement of this theorem before I start proving it? No? Okay, so to prove this theorem, I need this theory of anodyne extensions. So this is the part which is not in the notes yet, but you can find it in the book of Gers and Jardine. Okay. All right, so a class M of monomorphisms in S set is saturated if it satisfies a bunch of conditions. So it contains all isomorphisms and it's stable under, so let me make sure, push-outs, retracts, arbitrary coproducts, and countable compositions. Okay, so maybe this will be a bit more clear with this definition. So for any morphism P, This is something that we have used a lot, is that if you take the class of map which have the left listing property with respect to P and you intersect with monomorphisms, this is saturated, right? So, well, there are two statements here, right? First of all, any class of maps like this is stable under push-out, retracts, arbitrary coproducts, and countable compositions. And moreover, you have to use the fact that in simplicial sets, monomorphisms, which are inclusions, are also stable under all these things, which is not obvious because, well, typically monomorphisms are stable under pullbacks, arbitrary products, and well, countable compositions, okay? But to prove that they are stable under push-outs and arbitrary coproducts, you have to use this statement that we did last time, you know, that injections in sets are split monomorphisms. And so you can define a splitting like this that goes in the other way around, and you have to use this fact. Okay. Okay. Is this okay, this statement? It's something we have seen a lot, right? And now if we have B, a class of monos in L sets, we define its saturation, MB will be simply the intersection of all saturated classes that contain B. Okay, so it's the smallest saturated class that contains B. Okay, you can check that if you take this intersection, it will be a saturated class. Okay. And so now we get to the core of the theory of anodyne extensions. So anodyne extensions were introduced, I don't know when exactly, I would say a few years after people really started to deal with model structures and so on. Because before that, there was a lot of hands-on arguments. Sorry, I will answer your question just after. So before there were a lot of how to say hands-on arguments, ad hoc arguments about simplicial sets, and the people realized that a lot of arguments could be made into the common framework given by anodyne extensions. So the statement I'm going to prove just after is something that people proved again and again and again a lot. You can put it in one common statement. Okay, so the question is, what does the lemma state exactly? I'm saying that if you take any morphism P, you take, sorry, yes, you take any morphism P, you take the set of maps which have the left lifting property with respect to P, and you intersect with monomorphisms, then this is a saturated class in this sense, right? This is what the lemma states. Okay. So whenever you take a morphism, you take the set of maps which have the left listing property, then and you intersect with monos because I only define it for monomorphisms. Then this is saturated. It's stable under push-outs, retracts, arbitrary coproducts, countable compositions, and it contains all isomorphisms. Okay. Okay. So I will define 3 classes of maps. So the first one is this one. So you can check that they are all monomorphisms. The second one is this one. Okay, it's a bit more complicated. I will draw a picture, right? So let me write it and then I explain. Including inside delta 1 cross delta n, where n is at least 0 and epsilon is either 0 or 1. Okay, so what is this? I can write it in dimension 2. So you take delta 1 cross the boundary of the simplex. So essentially, maybe I will draw it in blue. So you have something like this, right? It's some kind of prism. All right, but you have to think that it is hollow, right? It contains the front face and the two back faces, right? But not the interior. Then you have this part here, which I will draw in green. It depends which epsilon you choose, but it's either the bottom face or the top face, right? And you glue it along the common thing, which is, maybe I draw it in red. It's this part here. Okay, so you take the bottom face. So lambda 1 epsilon is some kind of horn, but of course you take lambda 1 and you forget one face, you just get a point. So it's either 0 or 1 inside the interval. And you take this bottom face and you glue it with the boundary of the simplex cross the interval. All right, so it's something like this. And it's included inside the whole prism. Yeah, you can think it's like a horn of a prism if you want. It's like a prism in which you have removed either the top face or the bottom face and the interior, right? It's something like this. It's clear from the picture that it will be some kind of acyclic cofibration, right? But this is and the last one is something similar, but where instead of the boundary of the simplex and the full simplex, you get just an arbitrary inclusion. Tac, comme ça. Inside delta 1 cross x, where epsilon is either 0 or 1, and y inside x is a subsimplicial set, right? So same thing, but instead of having a simplex and its boundary, it's an arbitrary subsimplicial set. And so the theorem that we are going to prove, it's not that hard. And as I said, it's really like before people prove the same kind of theorems over and over again. It's all contained in this thing, is that MB1 is equal to MB2 equal to MB3. So the saturated class generated by either of these is the same. And definition, something which is in this class is called an anodyne extension. All right. Okay. And corollary, immediate corollary, is that vibration, by definition, vibrations are stuff that have left lifting property with respect to B1. Therefore, they have a right lifting property. Sorry, I said left. I should have said right. They have a right lifting property with respect. So this is pretty much by definition this. Therefore, it will be this and it will be this. Okay. So to check that something is a vibration, it is sufficient to check that it has the lifting property with respect to these maps or with respect to these maps. or the other way around. So there is a question, is it the real definition of anodyne extension or an ad hoc one? Yes, it's the real definition of anodyne extension. Yeah. Yeah, what I said about ad hoc arguments is that a lot of the time you wanted to prove some lifting property with respect to some thing like this or like this or like this, but you only knew the lifting property with respect to one of the others, and people just did it over and over again. This statement is just that it works all the time. Right. Okay, so it's time to have a little break. After the break, we prove this. And hopefully we finish proving the proof of the Quillen model structure. And if we have time, the adjunction with Quillen equivalence with topological space. All right. Recordings. Okay, so during the break, someone asked for clarification about this. So maybe the picture for n equals 1 helps better. So this blue part here is hollow, right? It's a tube. Second question that was asked is, can you define this in any model category? Well, in some sense, yes and no, but in the end, we will see that these are just acyclic cofibrations, and it's just a way around the fact that we don't know yet that we have an model category, so we cannot really talk about acyclic cofibrations. So there is a final question. What is K-horn in general? What do you mean K-horn?
Because if we want a definition that is can be extended to other preshift category, what we use is that it's MB1 of one inclusion, one particular inclusion.
Ah, yes. So for other categories, I have to admit I don't know at all. For this, I don't know. Yeah. So someone is giving les préfaisceaux comme modèle de type d'homotopie as a reference in the chat. So check this out. But for myself, I don't know. Okay.
What is the point of the enrichment? What is giving us the enrichment lemma with the adjunction with the product? And
you are going to see it's going to prove that. So here we are using this enrichment, right? And we are going to use anodyne extension to prove that simplicial homotopy groups are the same as classical homotopy groups of the geometric realization for fibrant sets. It's like something auxiliary.
Okay, and just in general, to have an enrichment in general, what is giving us?
This is a very broad question, right? It's really dependent on your category. It's not like this is a particular case where you have a Cartesian closed category. Not all categories are Cartesian closed. It's really like a whole field of mathematics, right? Enriched category theory. So I cannot really answer your question in a nice way, but
that does not solve some practical things where I don't know, a class of problems. Okay.
You mean enriched category theory?
The adjunction given by the enrichment.
Yeah, as I said, this is a situation where this is called a Cartesian. Maybe I can write it. Where is the statement? Here, it's Cartesian closed model. Not model, just a category. This is just a very nice setting to do a lot of categorical stuff. It turns out that simplicial sets have this structure, but yeah, to solve actual problems, it's really dependent on what category you are working with. I can't really give something. a general answer to this.
Last question. We can put one way to speak of model categories in terms of monoidal category. Monoidal model category. And
yeah, so there is something called monoidal model category. Is when you have a monoidal category with extra conditions.
Okay, and is it interesting to consider monoidal and with an enrichment model category, or?
Yeah, sure. You can. There are a lot of things that you can do. I cannot cover everything in this course, but yeah, you can have like enriched model categories, monoidal model categories, enriched monoidal model categories.
Okay.
The whole world is open to it. Yeah.
Okay. And Simplicial set, we can put an enriched monoidal model.
Yes,
category?
yes. The statement I'm proving is one that is necessary to show that it's a monoidal model category.
Thanks.
Yeah. Okay, so let me prove the theorem. The fact that MB2 is equal to MB3 it follows from the fact that C is equal to I cell. So it follows from the fact that to get X from Y, you can get it by gluing simplices. You can start from Y and then glue simplices along push outs and so on. So I will not write down the details, but it's a tiny exercise to show that this implies this, right? So let us prove that MB1 is equal to MB let us prove that MB2 is included in MB1. So we want, so it's enough to show that delta 1 cross boundary union lambda 1 epsilon cross delta n included in delta 1 cross delta n can be written as something which is an MB1. All right. So what we are going to do is exhibit this map as obtained from push outs along maps like this along and compositions, right? Okay, so essentially the idea is that we are going to take our picture here and we are going to see that to get from this to the full thing, right? The product of a full triangle with the interval, or maybe this one, it's clearer to get from this to the rectangle, we can glue simplices. And basically the idea will be that if we start from this, I wanted to do it in dimension 2, but dimension 1 is even simpler. Essentially, we are going to glue first a simplex like this along this horn, right? Right, this is a horn, and we glue a simplex along it. Then we have a new horn, and we glue another simplex, and we get to the rectangle. So this is all we are going to prove. We are going to prove that we can get from this to this just by gluing simplices along horns. Okay. So there is one way of doing it, which is not that bad. So you define Hj from delta n plus 1 to delta n cross delta 1 by 0, 0, 1, 0, and so on, up to J0. Then you go to J1, and then you continue and you go to N1. So in our case, so this is an n plus 1 simplex inside the product. So for example, n equals 1. We have our rectangles like this, so 0, 0. This is 1, 0, 0, 1, 1, 1. H0 is when you go up at 0 and then you continue, or the other one is this one. This is H1. If you want to do it for n equals 2, you have a prism like this. H0 is when you go up and then you continue along the simplex. This is H0. H1, you go along the simplex, you go up at 1 and then you continue. And H2, you go up at 2. Okay, and this defines n plus 1 simplices inside the full prism. So for example, this one defines this one, and this one defines this one. And so the statement is simply that you can obtain delta 1 cross delta n can be obtained by gluing, can be obtained from boundary cross delta 1 union delta n cross lambda 1. I'm just going to do it for 1. To do it for lambda 1, 0, you just have to reverse some rows by gluing simplices along horns using HJs. So for example, you have it's a bit annoying to write, so let delta n cross delta 1 j be the smallest subset of delta n cross delta 1 that contains several things. First of all, it has to contain delta n cross delta 1 union delta n cross lambda 1, 1, and H0, blah, 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 up to Hj. So delta n cross delta 1 minus 1 is equal to delta n cross delta 1 union delta n cross lambda 1, 1. And we have to go up to delta n cross delta 1 n, which is delta n cross delta 1, right? If you glue all these extra simplices, then you get to the full thing, right? And now we can obtain a push out like this. So it's a bit technical, but hopefully the idea is clear. I just want to write down the details. So this is a push out where this is Hj plus 1. So to get from 1 to the next, you just do a push out along a map like this. So to get from the first one to the last one, you do in total n plus 1 push outs. So for example, here you can see to go from this part, this U-shaped thing into the full rectangle, you have to glue 2 simplices. First, you glue along this horn, the bottom one, and then you glue along this horn, the new simplex. And here you glue first along the blue thing, the blue simplex, then the green thing, then the red thing. And well, you can check the details. In the end, it all works out. Okay. So there is a lot of combinatorics to write down the correct formulas, but visually it's pretty clear what's going on, right? So is this okay for everyone? So you start from this space and you glue along horns a bunch of n plus 1 simplices in order to get to this space. And so therefore this map is obtained as a composition of push outs along maps from, so let's recall what we are trying to do. We want to prove that this map is in the saturation of this set. And we have proved that it can be obtained as a finite composition of push-outs along maps like this. So it is in the saturation. Okay? Any questions? Okay. So now let's prove that the other way around, that MB1 is included in MB2, so i.e. Lambda nk to delta n is in the saturation of, well, the maps from before, so B2. So these kind of maps. Okay. So now we are not going to prove it that it's a push out. We are going to prove that it's a retract. Okay. So I also draw some pictures. So we have a retract diagram. Okay, it's going to be also a bit, it's a lot of combinatorics, right? But in the end, it's not very complicated. So this is included inside lambda n k cross delta 1 union delta n cross, sorry. Here it should be the boundary. Cross lambda 1, 1. So this is for k less than n. If k is equal to n, you have a similar picture, but I'm not going to do. And here this is rk, and here this is rk. You go here to lambda nk, and here you go to delta n. So this map belongs to B2. Right. So if we can prove that we have a retract like this, then we are done. Okay. So here it's just the standard inclusion. Now we need to define I. So I is the inclusion where you go to lambda nk inside lambda inside the boundary, and then you include inside delta 1 cross delta 1 union delta n cross lambda 1 1. Okay, and rk is simply the map that, so this is a map from delta n cross delta 1 to delta n. So I'm going to write it like this. And I'm going to explain. Okay, so let me explain what I've written here. So this is a map that takes two parameters, right? One from delta n and one from delta 1. So this is the delta n and this is the delta 1. And you have to produce an element of delta n. So just one number from 0 to n. And this is this map. Okay? And you have to take that this induces, its dual induces a simplicial map, well, not dual, but the induced map on simplicial by the co-simplicial structure is like this. And you have to check that it restricts here to lambda nk. So this is a lot of combinatorics that is probably not very meaningful, but let me draw a picture. So for example, let us show that, just to show you what's actually going on, let's show that delta lambda 2 1 included in delta 2. So this is this horn inside the full simplex. can be obtained as a retract of a map like this. Okay. Okay. Sorry. There is a tiny mistake here. It should have been at the beginning lambda nk. And so this map is not in B2, it's in B3, right? Here it's the sub-simplex lambda nk. Yeah, I thought there was something strange. But as we proved, MB2 and MB3 are the same. Okay, so what is lambda 2, 1 cross delta 1 union delta 2 cross lambda 1, 1? It's something that looks like this. So you have 0, 0, 1, 0, 2, 0. And you have the same thing at the top, but with 0, 1, 1, 1, 2, 1. Okay. The bottom face, you have the full delta 2. So this whole thing is included. So, okay, maybe I can do colors as before. So the red face is this thing. And the green, blue thing will be the rest. Sorry. It's going to be these two faces. All right. And our retraction here, you have to think about R1 is simply 0, 0, 1, 1, 1, 2. Okay, it stops at 1 here. So what does it do? It sends 0, 0 to 0. So this one is stays here. It sends 0, 1 to 0. So it retracts this point here. It sends 1, 0 to itself, to 1, 1, 1 to 1. So it retracts like this. It sends also 2, 0 to 1. So it retracts here. And it sends 2, 1 to 1. 2, 2, sorry. So it keeps this thing here. So it retracts like this onto a horn that looks like this. 0. Okay. So you collapse this whole thing to the 0. You collapse these three things to the 1, and you keep this one to the 2. Okay. And so you check that it is indeed a retraction. Okay, so I realize this is going a bit fast because there is a lot of combinatorics involved, but really this is not that bad. If you just sit down 10 minutes and you write down the details, you can see that this intuitive pictures is represented by this map here. Okay. So any questions about this proof? No?
Pourquoi il y a deux applications sur le diagramme qui s'appellent RK?
So RK, this one is the restriction of this one to this subsimplex, to this subset.
Ok, d'accord.
And you have to check that the restriction to this thing goes to indeed the horn. Right. But it doesn't touch the missing face when you restrict to this horn. Which is just, you have to check it. Okay, so with all this, we have proved that the saturations of these three classes of maps are the same. Okay. Corollary?
Excuse me?
Oui.
Geometrically,
Yeah.
why don't we take just an uniform RK, K, not depending on K? I mean, we could take écraser le delta n croix delta 1 sur delta n en bas ou en haut?
Le problème, c'est que, so the question is why we don't take the same RK every time. The problem is that precisely this is that we want to check that this RK, when you restrict it here, you don't touch the missing phase. So you have to find this retraction in a way that you don't, for example, here, I don't want to touch this one, right? And here you see there is no nothing between, like the composition of these two is not touch, no edge is sent to this edge, right? And when I restrict here. So that's why we don't take, we cannot take the same one every time.
Okay, merci.
Okay, so as a corollary, we have a very nice statement. So if I from K to L is anodyne and Y into X is any inclusion. So let's call this one I and this one J. Then you have this map that I define like this, I square J, which goes from K cross X union L cross Y along K cross Y into L cross X is anodyne. Okay, so a generalization of what we proved before. And the proof is a little bit subtle, right? I'm going to write it and you are not going to be sure if I proved anything, but I did. So you consider the class M, which is the class of all inclusions I prime from K prime to L prime, such that I prime square J is anodyne. Okay, so all monomorphisms, all inclusions, such that the similarly defined map like this is anodyne. Well, I'm going to make two claims. M is saturated. It's not hard to check, but you have to do it. It's stable under push out, pullbacks, and so on. So actually, if you read my notes, you will see that I have the same lemma, but I prove it in some kind of ad hoc way. This is where the theory of anodyne extensions shines, right? You don't have to do it in an ad hoc way. And moreover, it contains delta 1 cross y prime union lambda 1 epsilon cross x prime included in delta 1 cross x prime for all y prime included in x prime. And essentially use associativity of the square. This is not as trivial as it sounds, right? I have defined this application, and I'm sure you can guess what I mean by associativity. The square is associative, and so you have a very complicated formula, essentially that follows from the fact that delta 1 cross x prime cross x is homomorphic to delta 1 cross x prime cross x. But for the associativity of the square, if you are looking either at I prime cross I second square j and I prime square I second square j, you are going to be thinking about, in the first case, okay, for this one, a subcomplex of this one, and for this one, a subcomplex of this one, defined in a similar manner. And the statement is that these two subcomplexes are actually equal. And so it follows that if you have this inclusion here, then by definition, it will contain because it will contain this map, because whenever you will have this thing here, you will land inside this class. All right. So whenever you take an inclusion like this, the square of it with J will be in MB3. So it will be anodyne by definition. And so therefore, this class M contains all anodyne extensions. And so therefore, the statement of the theorem is true. Whenever I have an anodyne extension, I square J is anodyne. Because M, a class such that for square J is anodyne, contains all anodyne extensions. Okay, it's a little bit subtle. I encourage you to take a little bit of time at home to think about it again. Okay. So there is a lot of abstract nonsense going on, but it's not completely nonsense, right? Okay, so now from this we can prove that I star P star from map Bx to map Ax cross map By map, what did I say? Sorry, this is Ay, By is a vibration. Okay. So we have to show that this map has the lifting property with respect to this. All right, map Ax, map By, map Ay. Okay, we have to find the lift. But using adjunction, so the statement we proved before, this is equivalent to finding a lift in this diagram. And again, I encourage you to actually check that this is equivalent. You have to find a map from delta n into map of Bx such that two things happen. First of all, when you restrict to lambda nk, then you get your map from Bx that you had before. And second of all, that when you post-compose, well, two things. When you post-compose by the map P, then you get the map from By that you had before. And when you pre-compose by I, then you get your map from Ax from before, right? So essentially, I'm saying that to commute here, it's one condition. To commute here, it's two conditions, right? You have to land in the correct thing here and here. And so in the end, it means that you want to find a lift like this. Okay. But this is this one is anodyne by previous lemma. This is a vibration, and we prove that vibrations have the right lifting property with respect to all anodyne extensions. So there exists a lift. And so therefore there exists a lift here. Okay. Again, a lot of stuff going on, but you have to check a little bit. Okay. And so to prove similarly that if this is if I or P is acyclic, replace lambda nk by this one. Okay, we prove that if something has a right lifting property, yeah, but if something has a right lifting property with respect to this, then it is an acyclic cofibration. Okay, and then you use something in the other way around that you have to use something else to show that this one is anodyne. Okay. Okay, so going a bit fast, but it's really a matter of writing down the diagram and understanding well what it means for this to commute, for this one to commute, and for this one to commute. Okay, and in the end, you get something like this. Okay, any questions? So all of this to prove the following corollary. If I from A to B is an acyclic cofibration, P from X to Y is a fibration. X is fibrant. So if you replace Y by the terminal object, then map from Bx into map of Ax. In this case, this big square is reduces to this because Y is terminal, is an acyclic fibration. And similarly, if A is cofibrant, but every simplicial set is cofibrant, of course, and maybe I should call it B to make clear how it works. And X to Y is an acyclic fibration. Then map from AX to map of AY is an acyclic fibration, right? Okay. So here you just replace. Okay, I said I called it B. No, I should call it. You replace A by the initial object. And in this case, this thing here is trivial. Okay, so all of this is used to prove that simplicial homotopy groups are the same as classical homotopy groups for fibrant simplicial sets. So since you saw these before, but I think there were, I'm not sure the proof was in the book of Bruno. So let me briefly recall you the definition of the simplicial homotopy groups. And I promise we are almost done after that. So first of all, we need to define simplicial homotopies. So two simplicial maps F, G from A to X are homotopic if there exists a diagram like this. So you can view this as a subset of A cross delta 1 in two different ways, either by D0 or by D1. And you want for this to exist some H like this. Okay. So this is the notion of simplicial homotopy that you saw from before. It means that you can define some h on the edge of delta 1, such that when you restrict to one of the components, you get f, and when you restrict to the other component, you get g. Okay. So you could think that this is a cylinder of A. It will be, but we haven't proved yet that it's a model category, right? So we cannot already talk about this kind of thing. And we have a similar definition for relative homotopy. And now let X be vibrant. And we define, well, for some vertex V in X0, you can define pi n of X V as the maps from the simplex with the boundary collapse with respect to relative homotopy. Okay. So this you saw in the course of Bruno, right? Essentially, it's exactly what you think it is. Nothing funny going on. So you take maps from the simplex that are constant on the boundary, and you model by relative homotopy. Okay, so exactly the same definition as in topological spaces. And also pi 0 of X will be the maps from delta 0 up to homotopy. So essentially, you take vertices of X modulo, there exists an edge between the two. Okay, this is X0 modulo the relation maybe I should be more careful. Here it's G1 equals V. Okay, and just to be completely precise, because as you know, the relation is not necessarily symmetric, I will just exchange D1 and D0. So D1 is you miss one, so this is the inclusion as A cross 0. And here D0 is the inclusion as A cross 1. Right? Okay. So proposition you saw in Bruno's course. So if X is vibrant, then pi n of X V is a group which is abelian if n is at least 2. Okay. And so the proof is very visual. Let's say we are for n equals 1. Then what is an element of this? It's an edge, right? You have some alpha and you have some beta. And you go from star to star to star, where star is the base point. Or maybe I call it V. Well, to define the product, you just fill this horn. There exists a filling, and you take the missing face, and you get alpha times beta. All right, so there is a question before I continue. When the relation is not symmetric, we can define pi 0 of X by just considering the generated equivalence relation. You can do this. I guess for pi 0 it works. if X is not fibrant. For higher pi's, it's nothing good comes out of it. You would need to take like a fibrant replacement of X. I think for X, for pi 0, you can take what you say, the generated equivalence relation, and it works. In general, for pi n, nothing good. You have to take a fibrant replacement. But anyway, I only define it for fibrant stuff. This way I don't have an issue. All right, so, okay, so this defines the composition of two maps. To prove that it's a group, you want to define an inverse. And you fill this kind of horns, right? And to prove that it's abelian and associative, again, you fill horns in a nice way that I'm not going to explain. So if you want precise details, you look at my notes, but it's a fun exercise to try and do it yourself if you haven't done so already, to show how associativity can be proved using filling horns, how the fact that it's abelian can be proved filling horns, and so on. Okay, so first of all, a lemma. Pi 0 of X, defined like this, is isomorphic, well, in bijection really, to the path connected components of the geometric realization, okay, which is not obvious. So proof. So there exists a map from X0 to the geometric realization of X, which sends a vertex to the class of V0 inside X0 cross delta 0, seen as something inside the geometric realization. Okay? And it's pretty clear that by definition of X, this induces a map from pi 0 of X to pi 0 of the geometric realization. Because if you have two vertices in X that are connected by an edge, then in the geometric realization, they will be connected by an actual path, by something in delta 1, right? And so therefore, they will be in the same path component of the geometric realization. Okay? This map is surjective because delta n is a path connected. All right. Whenever you have an element of a geometric realization, so let's say you have xt in xn cross delta n, well, this t is connected by a path to x0 in xn cross delta n, but this is d0, blah, 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 d0, x0 in x0 cross delta 0. All right, this is an element which is in the face of delta n. So whenever you have something which is in the interior of a simplex, it's connected by a path to one of the vertex of the simplex. So therefore, it comes from this map. Okay. So it is surjective, and this map is injective. So how to show this? So for alpha in x0, let X alpha, sorry, I should say alpha in pi 0 of X, just to have something easier, is the subsimplex. So is the write it this way, subset of X such that all vertices are in alpha. So whenever you have a simplex in X, you can look at its vertices, right? You take iterated faces until you get to X0, and you ask for this vertex to be in alpha, which is a subset of X0, like the equivalence class of some element. Okay. Then X is the coproduct of the X alpha, because X is vibrant. Whenever you have a simplex, it has to be in some of the X alpha, because if you have two vertices of this simplex, they have to be in the same path component because they are connected by an edge. And so every element of X is in one of these simplicial sets. And these form simplicial sets, subsimplicial sets, and they are not, there is nothing between the two, right? There is no edge that connects elements of X alpha for different alpha. Okay. So moreover, pi 0 sends the disjoint union to the disjoint union. This is easy to show. Okay. So why? Because the X is vibrant? It's just because if you have well, you want to say it like this. Just to say that this equivalence class is symmetric and transitive and reflexive, right? But it is actually, yeah, it's basically just to be able to talk about pi 0. You are right. It's not really necessary at this point once the equivalence class is known to be transitive, symmetric, and reflexive. All right. All right, so okay, this is not what I wanted to do. And the geometric realization of a disjoint union is the disjoint union of a geometric realization, because geometric realization is a left adjoint. And so it follows that we have a map like this from the disjoint union of pi 0 of X alpha all right. And so this map sends one element here to one element here and not more, right? This is just a point because this is path connected. Okay. So if you have, what I want to say is if you have two different elements of pi 0, then they must be sent to different geometric realization of X alpha. And in top, the disjoint union sends a in top, if you have a X like this, then pi 0 like this. All right. So if you have two elements which are sent into different components of the disjoint union in top, then they have to be sent to different path components, right? You cannot have a path component of X intersect with a path component of Y, right? So if you have two different elements here, then they have to go to two different elements here. Okay. So it's time to Or any questions before we stop, because it's time and I still have a little bit to show, maybe half an hour, but we are going to do Friday. So are there any questions about all this before we stop? Okay, so just to give you an idea of where we are going, from this and using the statement of before, this one, we are going to show by induction that simplicial homotopy groups are the same as traditional homotopy groups of geometric realization, right? First thing. Using this, we have a new characterization of weak equivalences as something that induces an isomorphism on simplicial homotopy groups for fibrant objects. And using this and the theory of anodyne extensions, we are going to prove the lemma that we haven't proved yet, which is, where is it? It was at the very beginning. It was this one, that acyclic fibrations, and we are only going to do it for a fibrant source and target, have the right lifting property with respect to elements of I, so boundary of n, including in the simplex. So this will finish the proof that we have a model structure. So we are not very far from the end, right? But as you can see, it's quite involved, right? It's more complicated than chain complexes. And then, as a corollary of everything we have shown, we are also going to prove that this adjunction here is a Quillen equivalence, right? Okay. So this is where we are going. Then we are going to talk a little bit about Dolcan, just very brief, and then we are going to start rational homotopy theory. Okay. All right. So there is a question in the chat. A morphism is called anodyne if it has a left lifting property with respect to all can fibrations. Yes. Well, we proved it at some point. It was somewhere. Yes, it was here. Yeah, no problem. It's not, there was a lot of stuff going on today, so as I said, there are really some things that you should sit down at home and try to do on your own. I cannot, like, for example, all these retractions, all this. I know you did it last semester, but still, probably you should write down the details again, because it's a fun exercise and it will be useful for higher categories also. Right. Okay, so any more questions before I stop the recording? No? Okay, so I will stop.